For our physics project today, our task is to find the ratio of heights at which a roll of toilet paper unrolled and a roll of toilet paper dropped reach the ground at the same time. To do this, we will be using the following physics law. Conservation of energy, which is defined as initial energy is equal to energy final, where in this case, energy initial is potential energy and energy final is rotational and translational kinetic energy. For our experiment, we measured the height of the toilet roll being dropped and the inner and outer radius. So we chose to drop the toilet paper roll from 2 meters high because 1 meter was not enough of a time discrepancy for us to time, and when we measured the inner radius, it was about 2.65 centimeters, which was equal to 0.0265 meters, and an inner radius of outer radius, or big R, of 7.23 centimeters, which is equal to 0.0723 meters. So when we calculated the time needed to drop the regular toilet roll, we use conservation of energy, which is energy initial is equal to energy final. Energy initial is potential energy, so we used mass times gravity times height, which is equal to the kinetic energy, which is 1/2 mv squared, or mass times velocity squared. The two masses on each side cancel out, therefore we get an equation of gravity times height is equal to 1/2 velocity squared. And when we plug in all our numbers, we get 9.8, which is a constant for gravity, times the height of 2 meters is equal to 1/2 velocity squared. And when we isolate v, we get v squared is equal to 39.2, and when we take the square root of that, we get velocity is equal to 6.261 meters per second for the dropping the roll without unrolling it. After getting a velocity, we use the equation of delta y is equal to v plus v naught divided by 2 all multiplied by t. So we know that delta y was equal to 2 meters, which we set up here, and then we set the rest equal to the numbers that we got right here. We know that v naught is equal to 0 because we were just holding it in the air, and v final is what we calculated right here and divided by 2. So then when we calculate t, we get t is equal to 0.6389 seconds.
To calculate the height from which we should unroll the other toilet paper roll, we also use conservation of energy, which is energy initial equals energy final. So energy initial was potential energy, mgh, equals 1/2 mv squared, which was translational kinetic energy, plus 1/2 moment of inertia times omega squared, which is rotational kinetic energy. So we expanded moment of inertia into the equation that was given us, which is 1/2 m times small r squared plus big R squared, and we also canceled out the m's because they were the same on both sides, which left us with gh equals 1/2 v squared plus 1/4, which is these two halves times each other, times small r squared plus big R squared, times the omega that we expanded out into v squared over r squared. So then we plugged in number values, the constant for gravity, and then the radiuses that we measured. And once we solved for those a little, we got 9.8h equals 1/2 v squared plus 0.00148 times v squared over 0.0265 squared. So we then divided 0.00148 by this value to give us 2.11 times v squared. We added together these two v squared to give us 2.61 v squared, and then we expanded v squared out into delta y over t, which is all squared, which allowed us to cancel out this y and then this y squared. So we were left with 9.8 equals 2.61 times delta y over t squared. We plugged in the time value that we had calculated from our last step, which should be the same for both rolls by the time they hit the ground. We calculated that out, and then by the time that we'd finished solving for delta y, we had 1.533 meters, which was the height from which we would unroll the second toilet paper roll. Our results, though very slightly off, confirmed for the most part our calculations. The timing matched up with the time we had calculated, 0.64 seconds, and any discrepancy in the time both rolls hit the ground could be attributed to human error. We also made the assumption that both rolls had the same mass, radius, etc., which may not have been true, particularly the mass and radius, as after messing up the test, we had to rip off a few squares of toilet paper, which could have contributed to a discrepancy. Nevertheless, we consider our experiment successful.